Chapter 4, Making Sense of the Universe, Understanding Motion, Energy, and Gravity. So we wanted to know uh, how do we really describe an object's motion and how is mass different from weight? Let's take a look. So when we wanted to describe an object's motion, we can talk about its speed, which is the rate of change in distance with time. And the unit for that is meters per second. So for example, when I say an object is moving 10 meters per second, means in every second it is moving 10 meters. Okay, so 10 meters in every 1 second interval of time. If you wanted to add a little bit more information to our speed, we can talk about the velocity. And the velocity is the speed plus direction. So not only you need the value or an amplitude for the speed, but you wanted to talk about its direction as well. For example, 10 meters per second in a specific direction, north, south, east, west, whatever. So velocity is a vector. In other words, not only it needs an amplitude, it needs to have a direction associated with it. Acceleration is any change in the velocity, and it has a unit of meters per second per second. So any change meaning change both in the amplitude, or how much it is, and in the direction of it. For example, let's say that you're going 10 meters per second, and then suddenly you decide to go from, instead of going east, you want to go west. So you're not changing the actual number here, but you're changing the direction. So you do have an acceleration associated with your motion. Okay, and the importance here is the unit for that, meters per second per second. The change of velocity in every second. So that's why we are using meters per second square. Okay, so one of the common accelerating motions is that when something is freely falling, or acceleration due to gravity, and all falling objects accelerate in the same rate, no matter what it is. If you hold a feather here, or if you hold a piece of wood, they both accelerate in the same rate. However, the effect of air resistance could be different from feather to the piece of wood. So let's say that there is no air resistance for a second, and you're holding an object on top of a roof. At time starts, at time equals 0, you let the object fall down with a velocity equals 0. So you just let the object fall down to the ground. 1 second later, its velocity is 10 meters per second. Another second passed by, its velocity is 20 meters per second. Another second passed by, velocity is 30 meters per second. So you are gaining, or the object is gaining, the velocity of 10 meters per second in every second. Okay, so the object is gaining 10 meters per second of velocity in every second. In other words, it is 10 meters per second square, and that's the acceleration due to gravity. Any object that falls um, will experience the same type of acceleration, no matter what it is, no matter how big it is, how small it is, what the weight of it is. It is gaining the same with the same rate. It is gaining the speed at the same rate. So that's why we're calling it g, and we show it with g. In fact, the actual number for g is 9.81 meters per second squared, but we sometimes just use 10 for simplicity, okay? Now, this experiment, you can probably search for it on YouTube and see the video on yourself. But as Galileo showed that g is the same for all the falling objects. It doesn't really matter. So feather and hammer experiment that was done outside of Earth, so we don't have any air resistance in our way. You can search for it on Google and see the video for yourself. But they fall with the same rate. So they start with the same time, they hit the ground at the same time. The other very important factor, or the other very important definition that we have, is momentum. And momentum is mass times velocity. So P, we show it with P, momentum with P equals mass, show with M, velocity, we show it with V. And just make sure that this is velocity, it's not a speed. So not only you need an amplitude and magnitude for it, but you also need a direction, right? So I'm just using a vector here to indicate that it's velocity. Remember, there are two types of data that we have in physics. They're either scalars, which are just a number, no direction involved, and they are vectors. Not only you need to have an amplitude and a magnitude, but you also need to have a direction with it. Velocity is one of them. Momentum is the other one. On the right-hand side, you have a vector component. On the left-hand side, you should have a vector component. So momentum is also a vector component. So a net force changes the momentum. If you apply a force to a moving object, you're changing its velocity, so you're changing its momentum, which generally means an acceleration, okay? So if you apply a force to an object, you're changing its velocity, you're causing an acceleration, thus you are changing its momentum. So the rotational momentum of a spinning or orbiting object is known as angular momentum. If an object is rotating or spinning, like Earth that's rotating around the sun, or moon is rotating around the Earth, so we have angular momentum. So a thought question for all of you. Again, pause the video, read the thought question, answer, and then compare your answers with me, okay? Is a net force acting on each of the following objects? So if we go back, you might have seen this in your physics classes in high school, or if you take any physics class, you might have seen this before. P is mv, right? Momentum is mass times velocity. And if you apply a force, that force will cause a change of velocity, and it'll cause an acceleration, it'll cause the momentum to change. And if the momentum is changing, you have an acceleration, right? So Newton's second law is teaching us this. If there is a net force, okay, that net force is acting on an object, and the object is moving. That net force equals to the mass of the object times the acceleration of the object. So these are the two most important formulas here that we have. F equals ma, P equals mv. There's no difference between this m and this m. I just wrote this one capital. I don't know why, but regardless. So these two formulas are the ones that you're looking for. P equals mv, F equals ma. Okay. Now with that concept, let's go to the next question and talk about it. So let's see. So if is there a net force acting on each of the following objects? Answer yes or no. A car coming to stop. So when it's stopped, it has a velocity. When it's stopped, it doesn't have a velocity. Change of velocity is acceleration, right? Change of velocity is acceleration. If you have an acceleration, you have a force. A bus speeding up, velocity is increasing, so you have an acceleration, you have a force. An elevator moving up at a constant speed. If a constant speed, acceleration is 0. You're not accelerating. So if there's no acceleration, there is no force. A bicycle going around a curve. A bicycle going around a curve. Or somebody is going around a curve type motion, circular motion, right? This could be the same for someone, a kid in a merry-go-round in the park, in the playground, right? So remember, if the velocity is changing, you have acceleration. It doesn't matter if the magnitude of the velocity is changing or the direction of it is changing. If this guy is going around a curve, okay, curve line, the acceleration is in this direction. Sorry, the velocity is in this direction. The velocity here is in this direction. Here is in this direction. Here is in this direction. Okay. That's the velocity vector. But if you're going around a curve, the direction of the velocity is changing all the time. Remember, you have acceleration if something happens to velocity. Either its magnitude or its direction. So tell me, the direction is changing here, right? That means that you have acceleration. If you have acceleration, you have force. A moon orbiting Jupiter. This is the same concept. So yes. So let's take a look at the answers. Yes, yes, no, yes, yes. Okay, that's exactly what we thought. So let's take a look at the difference between mass and weight. Mass is the amount of matter that's inside an object. The amount of matter that is inside an object, okay, let's say your cell phone or your computer, whatever, it's the same amount of mass. It's the same number of molecules and atoms. If you take this cell phone or your computer or any object to another planet, you will still have the same amount of matter inside. Okay, so the mass is constant, but weight is a little bit different. Weight is a force that Earth is applying to that object. So weight is the force that Earth is applying to you. So F equals ma. Force. Now, what's the acceleration of gravity? G, exactly. Okay. So it is 10 times m, because this guy is roughly 10. Now, if you are going in an elevator and you're just standing in an elevator, nothing is happening, you're just sitting there, you won't feel anything. But if you're speeding up, going with an acceleration upward, then you'll feeling a little bit more heavy. You're feeling heavier. If you're speeding down, okay, you're feeling weightless. And if the cable just breaks, you'll just be in a free fall. So you don't feel you're completely weightless in the free fall. Okay, let me show this little thing to you. So I can, this little animation. So here, the elevator is in a stationary motion. Your weight is 140 pounds. Nothing weird. If the elevator is in a constant velocity, it's just still the same. You don't really feel anything. The velocity is constant. It's not changing. There is no acceleration. There is no external force. Everything is normal. But if the elevator is speeding up and accelerating upward, you're feeling a little bit heavy. I'm pretty sure that some of you have already, experienced this. If the elevator is going up with an acceleration, you feel a little bit heavy. What if it's going downward? You're feeling less heavy. It feels like weird, right? So your weight is less. And elevator in the free fall, you're completely weightless because you're freely falling. Just like you feel like an astronaut in outer space, that sort of thing. So you get the idea that what I'm talking about. The weight of you really depends on the circumstances. It really depends on whether you're going up with an acceleration, going down with an acceleration. Are you on Earth? Are you on another planet? It really, but the amount of mass, the molecules inside your body will be the same. Here on Moon, on Mars, wherever you are, right? So, and that's very important to note. All right, let's go back to PowerPoint. All right. So, a thought question: on the Moon, which one is true? The answer is B. Your weight is less because you're feeling there's a less gravity there, so your weight is less, and your mass is the same. Okay, your mass is the same. So a lot of times where people are complaining about their weight or saying like, oh, I don't like it, and it's like you can go to another planet and be completely weightless. So that's the difference between mass and weight. Mass is a number of molecules that is inside someone's body, and that will never change. okay, from planet A to planet B. However, the gravity that that planet applies to your body on Earth is something, on Moon is something else. So it really depends on the circumstances. Why astronauts are weightless in space? So there is gravity there, right? There is gravity there, but why do they? Where's the weightlessness comes from? So let's say that you're standing on the top of the tower, a very long tower, and you just jumping, and you're also moving with some sort of a speed, right? So you fall down. If you increase your speed, you'll go a little bit further. If you put a rocket and you attach yourself to a rocket, you will never fall down. So it will take zero amount of time for you to fall on the ground. In other words, you're always in a constant state of a free fall. So the weightlessness is coming from the constant state of a free fall. Here, when the cable breaks, you are feeling the weightlessness, right? Because it's freely falling. But what if you could attach a rocket to this and then having this rotate around the Earth? Not only you're freely falling, but you're also moving with a very high speed. So how much time would it take for you to freely fall? Hours, days. So that's why we have spacecraft that we're saying, okay, we need to adjust our motion with the spacecraft or satellites this much so we'll never fall on the ground. So we talked about what a speed is, what a speed plus direction is, what the change of the velocity means, which means acceleration. Momentum is mass times velocity, and force causes change in momentum producing acceleration. Now let's talk about Newton's laws of motion and what he did to change our view of the universe. There are three laws of motion, each of which are very, very equally important. Okay, so Newton's first law, but let's talk about what he was thinking. So he realized the same physics that operates in the everyday life on Earth is also true for the universe. It's also true for um, you know planets. The physics that governs the motion, the daily motions that we have on Earth, is also governing the motions of the planets. So that's what he was thinking, and that turned out to be exactly the truth. So Newton's first laws of motion is saying an object moves at constant velocity. An object moves at constant velocity, and that constant velocity could be zero. Okay, it's constant, right? It could be 10 meters per second. It could be 100 meters per second. It could also be zero, which means the object is stationary. It's not moving. So an object moves at a constant velocity unless a net force acts to change its speed or direction. In other words, an object, um, let's say a box, okay, and let's say that box is staying on a surface. An object, um, well, this box will stay stationary unless there is a force acting on it. And then if the force acts on it, it will start to move. So the velocity is not zero. If the box was moving initially with some sort of speed, okay, the box was moving initially with some sort of a speed, constant speed, it will continue, let's say 10 meters per second. It will continue with that motion unless there is a force acting on it, okay? In other words, objects would like to keep their type of motion. If they are stationary, they would like to stay stationary. If they are moving, they would like to stay moving. Second law, the force is mass times acceleration, or F equals ma. We have seen it a couple minutes ago. F equals ma. Okay, A is a vector, force is a vector. Third Newton's law, for every force or for every action, there is an opposite and equal reaction. For every action, there's an opposite and equal reaction. Okay? For example, you have a soccer ball and somebody kicks the ball. The foot of the player, soccer player, inserted some sort of a force to the soccer ball, causing the soccer ball to move. Soccer ball will do the same thing to the soccer player's foot. Okay? For every action, there's a reaction. All right. Thought question. Okay. So again, pause the video, think about this question, and answer it, and then play the video, and I'll talk about it. Is the force that Earth exerts on you larger, smaller, or the same as the force that you exert on Earth? Remember, for every action, there's a reaction in the opposite direction, completely equal. So with that idea, the answer is Earth and you exerts equal and opposite forces on each other. True. Another thought question, and this is true and false. So we have to read all of them. So the force of a car on a truck, so let's read the question first. So a compact car and a large truck have a head-on collision. Okay. Are the following true or false? The force of a car on a truck is equal and opposite to the force of a truck on a car. The momentum transferred from the truck to the car is equal and opposite to the momentum transferred from the car to the truck. And the third one that we have to find whether these are true or false is the change of velocity of the car is the same as the change of velocity of a truck. Let's take a look. The only one that's false is number 3. The rest of them are completely true. So the force of a car on a truck is equal to and opposite to the force of the truck on a car. For every action, there's a reaction equal and opposite. The momentum transferred from the truck on a car is equal to the opposite to the momentum. So these two are true, but the last one is completely false. Why? The change of velocity of a car is not necessarily the same as a change of velocity of the truck. The momentum, yes, or the momentum transfer, but since their masses are different, the mass of a car and the mass of a truck are different, so the change of velocity is not the same. Okay, I'm going to stop here for this part, chapter 4, and we will continue with chapter 4, part 2. Stay tuned. Don't go anywhere.